Welcome back to another episode of Tech Talk, where we dive into the intricate world of technology and data management. Today, we're exploring a crucial aspect of databases, replication. Whether you're a developer, a database administrator, or just a tech enthusiast, understanding how data replication works can significantly impact your system's performance and reliability. So, grab your headphones and let's get started. At its core, database replication involves creating copies of data from one database server, known as the leader, to one or more other servers called followers. This process is essential for ensuring data availability, fault tolerance, and load balancing. The leader writes a log of changes to the database, which is then sent to the followers. This log, often referred to as a write-ahead log, details the specific changes made at a low level, including which bytes were altered in disk blocks. However, this method has its drawbacks. The tight coupling between the log and the storage engine means that if the database changes its storage format, it can be challenging to run different versions of the database software on the leader and followers. This can lead to downtime during upgrades, which is a significant concern for businesses that rely on continuous availability. To overcome some limitations of traditional replication methods, we can use logical replication. Unlike physical replication, which is tied to the storage engine's internal structure, logical replication operates at a higher level, focusing on the data itself. In logical replication, changes are logged at the row level. For instance, when a row is inserted, the log captures the new values of all its columns. For deletions, it records enough information to uniquely identify the row, typically using a primary key. This method allows for greater flexibility, enabling different versions of database software to coexist and facilitating easier integration with external applications. Logical logs can also be used for change data capture, a technique that allows businesses to send database changes to external systems for analytics or indexing without impacting the main application. While built-in replication methods are often reliable, there are scenarios where more flexibility is required. For instance, if you want to replicate only a subset of data or need to resolve conflicts between different data sources, you might need to implement replication at the application layer. Tools like Oracle, Golden Gate, and Bucardo for PostgreSQL allow applications to read database logs and replicate data changes. This approach, while more prone to bugs than built-in methods, offers the flexibility to meet specific business needs. Replication serves several purposes beyond just data redundancy. It enhances scalability, allowing systems to handle more requests than a single machine can manage. By distributing read requests across multiple followers, businesses can significantly reduce the load on the leader, which is particularly beneficial for read-heavy workloads that are common in web applications. However, it's essential to note that this method typically relies on asynchronous replication. While this allows for the addition of more followers, it can lead to issues with replication lag, where followers may not immediately reflect the latest changes made on the leader. Replication lag is a critical concept to grasp. It refers to the delay between a write operation on the leader and its reflection on the followers. Under normal conditions, this lag may be minimal, often just a fraction of a second. However, under heavy load or network issues, it can extend to several seconds or even minutes, leading to inconsistencies in the data. For example, if a user submits data and then immediately tries to view it from a follower, they might see outdated information, which can be frustrating and lead to confusion. This phenomenon is known as eventual consistency, where followers eventually catch up to the leader, but not instantaneously. To mitigate the issues arising from replication lag, developers can implement various strategies. One approach is to read from the leader when users are likely to read data they've just modified. This ensures they see their most recent changes. Another method involves time-based strategies, where applications track the time of the last update to decide whether to read from the leader or a follower. If the follower is more than a minute behind, it might be wise to redirect the read request to the leader. Additionally, clients can remember the timestamp of their last write, allowing the system to ensure that any reads reflect updates made before that timestamp. For users accessing services from multiple devices, maintaining consistency across those devices can be particularly challenging, especially if their devices are routed to different data centers. Another issue that can arise from replication lag is the potential for users to see data that appears to move backward in time. This can happen if a user refreshes a page and receives responses from different replicas, leading to confusion when they see inconsistent data. To prevent this, applications need to implement strategies that ensure users don't experience this backward movement in their data interactions. In summary, understanding database replication is vital for anyone involved in data management. By grasping the concepts of logical versus physical replication, the implications of replication lag, and the strategies to maintain consistency, you can design systems that are not only robust, but also user-friendly. Thank you for tuning into this episode of Tech Talk. We hope you found this discussion on database replication insightful. If you have any questions or topics you'd like us to cover in future episodes, feel free to reach out. Until next time, keep exploring the fascinating world of technology.